On this video, we're gonna cover trigonometric equations. Now, trigonometric equations, just like any other algebraic equations, they consist of the left-hand side as well as the right-hand side, in which case the left-hand side should equal the right-hand side. Now, in an equation, we'll look for the value of the variable x or variable y, for which we will satisfy the equation. Same applies here. Here we'll look for the value of the variable theta, x, alpha, or beta, which will satisfy the equation. Now, those values will be represented by angles. So it can be 90 degrees, 30 degrees, 40 degrees, or whatever the angle is. And I'm just specifically choosing those because they're easy to come by. Now, we're going to talk about equations that involve quotient identities, correlations, as well as equations that involve factorizations. Now, your basic factorization that we will focus on here is simply your highest common factor, trinomial, and difference of squares. Now, you don't have to worry about the difference of cubes. We don't particularly deal with that. And we'll also do equations that involve reduction or using reduction formulas. So to begin, we'll talk about the principle underlying these equations. So this basic principle you have to use whenever you're given trigonometric equation involving the sine ratio, cosine ratio, as well as the tangent ratio. So the principle does not change, by the way. So all you need to do is to identify what ratio particularly you're dealing with for that particular problem, and then apply the specific principle. Let's go through some of those principles. Let's say you're given sine theta equals a. Now the a here is just a number. Now the number a should be between -1 as well as 1. Now that number should be between -1 and 1, but it can also equals to 1. Hence you see the conjunction inequality less than and equals to for -1 and less than and equals to +1. Now, if we use our interval notation, we can say that a is an element of, we use square brackets for part of the solution, -1 and 1. What we mean by that is the a involves any numbers that lie between -1 and 1, and -1 and 1 also being part of the solution. So this number here will be some number between -1 and 1, as well as it can be 1 and -1. But mostly, I've seen in my experience, it lies usually between -1 and 1. Now, if we have that, therefore, we have to solve for theta, that angle. Therefore, theta, we'll have to apply the inverse of sine. And then when we do that, remember in an equation, whatever we do on the left-hand side, we'll also do on the right-hand side. This is the inverse of sine, which will cancel the sine. Notice this thing is not the same as 1 over sine x. No, that's wrong. It is an inverse of a sine, but it's not the same as 1 over sine x. So it will be an error for you to assume that this is simply 1 over sine x, because it is not. So I just wanted to caution you as far as that is concerned. But it is an inverse of sine, meaning just like an x squared, a square is an inverse of a square root. If we can apply the square root, we can cancel this property as a property of cancelling that square, or the square root as a property of cancelling the square. And then I will find the square root of 4, which is basically 2. Now, if I apply this square, all I'm doing is getting rid of the square root. Or if I have a square root of 2 and then square that, basically will have 2, because the square will cancel the square root. Simple as that. So they're inverse of each other. So the same thing goes on here when we have sine, inverse sine multiplied by the sine. They're going to cancel each other. And if I do that on the left-hand side of the equation, I have to do it on the right-hand side of the equation. Just simply equations just work the same way whenever you're dealing with an equation. All right. So you're going to have theta equals sine second function or inverse sine of a. Remember, a is a number between -1 and 1, as well as equals to -1 and 1. So if it is equals to -1 and 1, it is still going to work out. But if it's some number -2 or +2, it's not going to work out. Any number above 1 and below -1, those numbers won't work out. If you punch your calculator, you will see something such as undefined or math error. So you just want to work with those numbers, maintaining that they lie within that. This is what we call the domain of your age. Now, it has a restriction in a sense. So I'm going to punch theta equals, if I'm looking for theta, I'm going to punch sine second function, that's second function of A. Now, second function basically simply means that you punch a shift on a calculator and then you punch sine. If you punch shift and then sine, something like this will come out. Let me just show you in my particular calculator. So if I shift and then sine, something like that comes out. And then whatever number that I'm going to put there, that's what's going to come out. All right, I even put that number, so that hence the calculator say the operation is not supported. I just wanted you to see the symbol as it comes out there. So now, that's what I'm going to do. If I punch a shift and a sine, I'm going to have this. If I place that number here, or let's say that number is 0.2. And then, so let's say shift and then sine, that's going to be 0.2. And then you see some angle pops out there. That's 11.53 or 54, rounded to 2 decimals. Now, that's the most important thing that you would need to do. So this angle here is not your solution to the angle, but it's what we refer to as the reference angle. It's not the solution for theta, but it is a reference angle. So your solution or your general solution is going to be theta equals the reference angle, the number that you got right there, punching shift sine, whatever number they gave you here, plus 360 times k, where k is an element of integer. Now, you take 360 here is simply the period of the function. This is a graph, by the way. It's simply the period of the function or the sine graph. So what we have will be 360 times k. Exactly what is k? K is here an element of integer. Now the integer that are going to be substituted there mostly will be -3, -2, -1, 0, 1, 2, and 3. But hardly -3 and +3. By the time you get to -2, -1, 0, 1, and 2, you would have found all the solution which will lie within a specific domain. Now, what do we do then? I said that the reference angle is not the solution to theta, but it is part of the solution to theta. So what we're going to have to think about is an oscillation type of question, type of case, if you may, where we keep rounding around same points. And the idea of oscillation is that we will get multiple solutions. If we land into this position, we will get many points. We will come back to this point many times as we oscillate or go round and round. So hence we have to limit the solution within a certain interval or domain. So usually I think you've seen where they wanted you to solve for theta being element of -180 degrees to 360 degrees. By that they mean that you can get multiple solutions as you oscillate around. So there are many times you come back to that point. But they want the ones that are limited within -180 to 360 degrees. Simple as that. So that's what K is going to be used for the most part. I hope that does illustrate the point. Now we'll see as we go on what exactly that is. All right. The second solution for theta here, as long as you're working with sine, you're going to say or theta is going to equal 180 degrees, and then I'm going to subtract my reference angle plus 360 times k. K is an element of integers, or z. All right, you keep writing k is an element of integers. As long as you make this statement, you're going to have to say k is an element of integers. All right, so that's what you're going to do when sine is involved. But what about cosine? If you're dealing with cosine theta, equals a. Again, a is an element of -1 and 1, and also equals to -1 and 1. All right, so this is key. If it is beyond those or outside of that interval, it's not going to work. So the theta will be cosine second function, or second function cosine a, or shift, and then press cosine, and then something like that will come out. Now if something like that does come out, you're going to press this number, whatever number that is, that will give you. All right. And therefore theta for more general solution will be the reference angle. Cosine negative or shift cosine a is going to give you your reference angle. This is your reference angle. Now the general solution for that is going to be plus. But by general solution, I basically mean the solution which is more general. It doesn't lie within a specific interval. Now, there are sometimes restricted solutions, as I've indicated to you earlier on. So in this case, theta is going to be equals plus or minus your reference angle plus 260 times k, where k is an element of z. All right. Again, we use the period 360 for the cosine. All right, and that's it. What about tangent? If you're given tangent theta equals a, now for the tangent, we're going to work with it a little bit different compared to the other ones. The a for theta, for tangent, can be any number as long as that number is a real number. So a can be an element of real numbers. We can go from negative infinity all the way to positive infinity with a. So any number will work as long as it's a real number and not a complex number. Now, complex numbers aren't going to work. All right. By complex numbers, I mean, for example, a square root of a negative number, a square root of a -4, for example. That's a complex number. It's a non-real number. So I'm going to do the same thing. Theta is equals to tangent second function, or second function tangent a, in which case that's going to give me the reference angle. This is going to give me the reference angle. So for a more general solution, theta is going to be the reference angle plus 180 times k, where k is an element of z. You already know how to work with k, k being the element of integers from -3 all the way to +3. And then 180 here is the period of the graph. Now you can see that the period of this graph, or the tangent function, is different from the other two. Now, so these are the principles simply that you're going to need to apply throughout when you're working with your problems. Let's take some few problems, and I'm going to demonstrate what I mean by that. How can you determine the general solution for sine theta equals √3/2? How can you work that out? Now, we use the principle that we've talked about. Sine is involved, and we know we have basically two solutions. You can scroll up or go back the video and just check out how we worked it out, and you see it's going to be exactly the way I'm going to work this problem out. So what I'm going to do is I'm going to apply second function sine on both sides of the equation, or the inverse of sine, which is the arc sine. So theta is going to be arc sine that number, which is √3/2. Now the √3/2 should be a number, because it's taking the place of a. It should be a number between -1 and 1. And we can just simply punch a calculator to confirm that. So I'm going to say √3/2, and you can see the √3/2 decimals is 0.8660254038. I didn't have to read the whole number, by the way, but you can see it's some number between -1 and 1. It's approaching 1, by the way, so it's more closest to 1, but it's not equals to 1 or greater than 1 for that matter. So as long as I say that, I'm fine. Whatever I'm trying to work with is going to work out. So I'm going to say theta equals. Now what I need to do is to get the second function and then shift second function, which is your shift, and then it's going to be your sine, and you see something like that comes out, like a negative sine to the -1. That's an inverse of sine. And what I'm going to do is simply to find that number, which is root 3 over 2. So that's going to be root 3, and then that's going to be divided by 2. And 60 comes out. Now the 60 that comes out is the reference angle. It's not the solution to theta. This 60 is a reference angle. All right. For a more general solution, the theta is going to be 60 degrees, which is the reference angle, plus 360 degrees times k, where k is an element of integer. Like I said, don't forget to write k as an element of z. Or, whenever I'm working with sine obtuse solution, the theta will be 180 degrees minus the reference angle, which is 60 degrees, plus 360 degrees times k, 360 being the period, and then k is an element of z. All right, so this one is done, but I need to simplify this one, meaning I need to resolve 180 minus theta. So once I come there, just basically it's going to be 180 degrees minus 60. That's going to be 120 plus k times 360. You can say 360 times k or k times 360 is the same. I do not have to write k element of z anymore because I've already done it here. All right. So here I was just simplifying or maybe resolving the 180 minus 60 degrees. All right. I hope that checks out. Let's take the next example. How can you resolve the equation cosine theta equals 1 over 2? Now you know the principle underlying the cosine theta ratio when you're working with trigonometric equations. All I need to do is to equate theta to the second function, cosine 1 over 2. 1 over 2 is 0.5. It is a number that lies between -1 and 1. All right. So theta is going to be, this is more like arc cosine 1 over 2. And the inverse of cosine 1 over 2 is more like when you think of cosine 60 degrees, which gives you 1 over 2. When we want the inverse, we're just going to go in reverse. So when we apply an inverse of that, look at what's left behind. So if I say cosine negative to the -1 times cosine 60 degrees, I'm going to have to do the same thing on the right, and then there's going to be the second function. All right, you see this and this cancel, so this gives you 60 degrees. All right. So it's more like when you're working with reverse, especially with this type of numbers, which you get when you work your special angles. So that's where I know that from. So there's going to be 60 degrees. And then the 60 degrees here is my reference angle. All I need to do for the more general solution, theta is going to be plus or minus. Remember to put plus or minus. 60 degrees plus 260 degrees times k, where k is an element of integers. And now you're done. Let's go take another one. What about tangent theta equals a? 1. So the a is 1 here. Remember, for tangent theta equals a, the a here is an element of real number. It can be any number as long as that number is real and not a complex number. So we get a 1. But again, 1 is still within that domain of -1 and 1. So even if it was a 2 or 3 or anything, it was going to work. It doesn't have to be limited within that domain, but fortunate enough that it's within that domain. But even if it wasn't, we're still going to work with it quite fine. So theta is going to be tangent second function, or second function tangent 1. Now, when we press tangent 45 degrees on a calculator, we get 1. It means second function tangent 1 is going to give us 45 degrees. Simple as that. You just simply work in reverse. That's going to be 45 degrees plus, remember the period for this one is 180 degrees times k, where k is an element of integers. And you're done finding the more general solution. Remember here, I'm just simply working with general solution. I'm not working with solutions that are within a restricted domain or interval. We will get to those later on, but nothing is different. We just want specific solutions that are within a certain domain. But here we're looking for a more general solution. All right. So that's why I'm not substituting anything for k here. I'm just leaving it like that. Once you have k in your solution, that's a more general solution. A more specific solution within a certain domain won't have that, because we will substitute that for numbers such as -3, -2, -1, 0, 1, and 2, as well as 3. Right. How can you determine the general solution for cosine theta plus 10 degrees equals 0? Now 0 is a number between -1 and 1, and I'm fine with it. All I need to do here is to treat this thing as a whole. I'm going to apply the inverse cosine both sides, and then theta plus 10 degrees is going to equals inverse cosine of 0. Now theta plus 10 degrees is going to equals my reference angle will be all that. So if I punch that in a calculator, that's going to be shift cosine 0, and that's going to be 90 degrees. So I'm getting a 90 degrees as a reference angle. Remember, all I need to do for the reference angle is to simply place plus or minus if I'm dealing with cosine. The reference angle is plus 360 times k, where k is an element of integers. All right. So I want to solve for theta, not for theta plus 10. Now in that case, it means then I'll have to subtract 10 degrees both sides of the equation. So what I'm going to have is theta equals plus or minus 90 degrees minus the 10 degrees. Plus 260 times k. I do not have to keep writing k element of z. As long as I did in the first statement, I'm fine. All I need to do is to resolve the plus 90 minus 10, which is going to be 80 degrees, positive 80 degrees, plus 360 times k. Or the other one can be the minus 90 minus 10, which is going to be minus 100 degrees, plus 260 times k. Simple as that. So this is your general solution. Next up will be this one. Cosine theta equals sine 20 degrees. How can you resolve that? Now I just have to look for a few things. Here I have theta, which I need to solve. The cosine 20 degrees is not much of a problem. I can change this and work with that. All I need to do is to basically work with this part, the one on the right hand side. Now I can employ what we refer to as correlations. Right? All I need to do is to change this ratio, and I want it to look more like that ratio. So I'm going to have cosine theta equals sine 20 degrees is more like when I have cosine 90 degrees minus 70 degrees. All right. Remember, when we use correlation, this is going to be simply sine. That's 90 minus 70. That's going to be 20. That's going to be 20. And if I'm working with that, then I'm fine with the 20. 90 minus 70 is going to give me a 20. Should be minus 20. I think. Should be minus 20 degrees. 90 minus 20 degrees is going to give me sine 20 degrees. All right. But I know that 90 minus 20 is 70. So this gives me cosine 70 degrees if I want to work with the cosine. So that's going to be cosine 70 degrees. So now that I have cosine 70 degrees, I can go ahead and work out something. Now, this is going to be theta equals 70 degrees, therefore will be my reference angle. I just remove the signs here, the cosine rather, and be left with a 70 and a theta on the left hand side. So just remember to use your correlations in order to work out that one. All right, so what I'm going to do is simply to get I just need to show you something here so that you can understand what we talked about. We talked about being able to change this into its correlation. So if I have sine 90 degrees minus 70, right? This is going to give me sine 20 degrees. All right, but this, working with the correlations, is the same as cosine 70 degrees. So that's how I worked it out, for more exact, accurate way of just showing that. All right, so this is going to be plus or minus 70 degrees times or plus 360 degrees times the k, or k element, where k is an element of z. Now that we're looking for a general solution, so I'm done. Another one is where you have to solve for x, where you have sine 2x equals 0.8. 2x minus 15 equals 2.8. All I need to do is to apply my inverse sine both sides, and then on the left I'm going to be left with then equals second function sine 0.8. You take a calculator and check what that is. So I'm going to have second function sine 0.8 is 53.13 degrees. So that's going to be 2x plus 15 degrees equals, that's going to be 53.130 degrees. The 53.130 degrees is the reference angle. So I'm just going to add 360 times k to the reference angle, where k is an element of integer for the solution, general solution. Now remember, the next thing I need to do, as long as sine is involved, is to take the, this was a minus, is to take the reference angle and subtract it from 180 degrees. That's going to be 53.13 subtracted from 180 degrees plus 260 times k, where k is an element of integers. I'm running a little bit out of space there, but I'm just going to work it out like that. All right. So now that I'm here, I'm looking for the x, not the 15 degrees. So I'm just going to simply add 15 degrees and also add 15 degrees on the right hand side. Now because here it was 2x minus 15 degrees, just to make sure that we are on the right path. So on the left I'm going to be left with 2x. Here I'm going to have 53.13 plus 15 degrees. So I'm just going to take the 53.13 and plus my 15 degrees. I'm going to have 68.13 degrees, and then plus 360 times k. I do not have to keep writing k element of integers. I'm fine. Or here, remember, I'm going to add 15 also on the left and add 15 on the right. That and that will cancel. So I'm going to be left with 2x equals, remember I add 180 minus 53.13 first, and then I'm going to add 15. So what I'm going to do is to have 180 degrees minus 53.13 and then plus 15 degrees. That's going to give me 141.87 degrees. So that's going to be 141.87 degrees plus k times 360, where k is an element of integers. All I need to do right now is to divide throughout this equation by 2. And if I do that, I'm going to get x equals 68.13 divided by 2. Let's see what that gives us. So I'm going to have 68.13. And I'm going to divide that by 2. It's going to be 34.067 or 34.07. 4.07 degrees. And then plus, again, I have 360 divided by 2. So I'm going to have 360, and I'm going to divide it by 2, which is going to be 180 degrees. So that's going to be 180 degrees times k. These are a product. So if I divide by 2, I've also divided by the k by 2. So it's going to be 180 times k. All right. Or I'm going to come for this one. It's going to be divided by 2, and everything on the right is also divided by 2. In which case I have x equals 141.87. So that's going to be 141.87. I'm going to divide that by 2. So that's going to be divided by 2. It's going to give me 70.94 degrees. So I'm going to have 70.94 degrees. And then plus 360 divided by 2 is 180 times k. And that's my general solution to that. So that's basically how you work out those kind of problems. Now I want to take a look at the problem that involves the equation where sine theta and cosine theta are involved, and I'm going to have to work with my quotient identities. All right, let's say we have sine theta equals cosine theta, and I need to solve for the trigonometric identity. So I see the sine theta and cosine theta are both involved. All right, so there is no working with the correlations here. I just need to work with what I'm working with. All right, all I need to do is to use the quotient. I know that tangent theta is going to be equal to sine theta over cosine theta. So that's what I'm going to do. Let me rewrite the equation again. Sine theta equals cosine theta. All I need to do is to divide by cosine theta and also divide by cosine theta. These on the left hand side is going to be your tangent theta. So the tangent theta equals that, and that will cancel, will be a 1. We've already worked with tangent second function 1, but we've got a 45 degrees. So theta is going to be 45 degrees plus k. Remember, this is multiplied by 180 for the, this is 180 for the period, where k is an element of z. So I'm done. I just needed to simply know how to work with that.